You have anything you want to ask?
What's student ID?
Never mind. Leave it blank first. Because I think they got some problem. Student will register, then you have a student ID. Okay. But actually it's your NRIC. Okay. Anything you want to ask? Any questions you want to ask? Yep.
Yeah, do we come first?
I see.
Acid, right? There's this titration graph thing that is very confusing. I can go through how to do it.
Okay.
Yeah, like how to find the pH point for all the buffers.
pH point for all the buffer. Yeah, okay, sure. Then today how many topics you want to do?
You see how much we can just cover. Just for the
Okay, then my video,
yeah, I will go watch.
I got to, I don't know what title to put. Or maybe I just cut it into 2 parts or something. Okay, so what do you want to do first? Acid, base and stuff, is it?
Yeah.
Okay, can I take a look?
Yeah, the weak acid.
How about the rest?
Where is it?
Rest is okay, right? Rest is okay, then how come you have problem here? Okay. Very simple actually. Okay, we have Ka, right? Okay. You know, we other than K, we have Kc, with Kb, with Ksp. Then we come to Ka and Kb, right? We still have one Kw. Okay? Actually, they are all from Kc with some adjustment. The adjustment is that, and you know where does Kc come from? Kc come from the rate of reactions, the K forward over K backward, those things. Okay. K forward equal to something, K back, okay. Rate forward equal to K forward something, rate backward equal to K backward something, okay. When the two rates are the same, we equate them, and then chemist says constant one side, variables another side. So all the constant bring one side, divide, and all the variables throw another side, you got, and then they will label the whole constant as Kc. Okay, so any K anything is actually a constant that they just try to keep throwing all the constant to one side. So from Kc to Kp, right, you just take in all the RT, okay, because PV equal to nRT, right? So therefore N over V, right, equal to P over RT. Okay? So therefore the concentrations, number of mole per unit volume, concentration equal to P over RT. Okay? So therefore, if you say concentrations equal to P, and then you have 1 over RT as extra constants. Okay? So this is why in your Kp there is everything with P, P, P. Okay? But why is it called Kp? Because it absorbs all the 1 over RT things.
So it's Jc times 1.
So whenever they add in some extra constant to a left-hand side symbol, they will rename the symbol to another subscript. Got it? Okay. So the Ksp also actually is from Kc, but you have the right-hand side of the bracket and left-hand side you have another thing. Okay, it's supposed to type this over this, right? But this is gone, right? Okay, why is it gone? Because in saturated solution, this is a constant that you cannot change. Okay, this is the dissolved amount or in the equilibrium amount which is will not change. So we absorb inside the Kc and then we label everything as Ksp. Okay, so K and Kp also the same thing. They absorb something. Okay, so it's supposed to have an acid, then dissociate with H plus plus A minus kind of things, right? But actually it's not. Okay, you're supposed to have an H2O here, and this is supposed to be H3O plus. Okay, when you have H3O plus, you have H3O plus and this and that, right? So the correct equation, I just try to give you a feeling. Okay, so that actually you realize that if you in front is okay, I don't think you have a problem in this if you understand all this. Okay, It's supposed Kc, right? You have your H3O plus and A minus, and then your HA, and then this H2O. Whereas the base, right? You have kind of things like NH3, H2O, then give you kind of things like. NH3, H2O, and then you have the NH4 plus, and then you have the OH minus. Okay. Therefore, you're supposed to have a Kc equal to NH4 plus, OH minus, and then you have NH3, and then you have H2O. Okay. But the idea is this: water. Okay, amount, okay, the whole solvent is water. Since the whole solvent is water, the quantity of water is kind of fixed, because it's just the density of water is how many gram per how many dm cube, and then use the gram divided by mR, so it's become how many mole in dm cube, so it's fixed. Density is fixed, so mole per dm cube is fixed. So this is a constant. Absorb it inside and we label it as Ka. Absorb this, time this together, they call it Kb. Okay, so that's K and Kb. So come back here. Okay, let's talk about titration things. Straight away go into the point. Okay, so just remember they actually follow the concept of Kc. Wow, what happened to this marker? Horrible. So straight away, okay, when you have strong acid, strong base, you neutralize first, and NaCl, right? Okay, so this is why we count things like first thing, if it is in room temperature and pressure, pH will end up at 7 at neutral point. Okay, neutral point. Okay, make sense? Okay, so the point is that all acid and alkaline is being reacted to form this and that. There's no more excess of acid, there's no more excess of alkaline. Okay, so from this kind of thing. So how do we define neutral point? Okay, I'm asking a very simple question. If you are the chemist, how do you define neutral point? When? Okay,
when reaction stop.
Reaction stop. Now when you just neutralize enough, reaction stop, right? You keep pouring, reaction still stop. Right? That's not very close, okay? So when is the just nice point that you think that you should define as? If you're the chemist, okay? Don't need to be too professional, okay? Because this is defined in a very ancient time, okay? So at the time they also don't have much calculations. They just define some neutral point. So what do you think? When?
Sharp increase in pH.
Stop increase in pH. Okay, drop the word pH, okay, make it even more generic than that. Yeah, it's good, okay. So what else do you think? When all the what is get rid by who or that kind of things?
All the H plus get rid by the OH.
Good, okay. So can I say is that if I have a 10 H plus here, I'm not talking about 10 mole, okay, let's talk about 10 particles H plus here. So long as you can remove these 10 H plus particles, it's going to neutralize, right? Same thing, okay? So let's make it very simple. But you will hear something like, when you have a strong acid with weak base, then up in the neutralization point, right, you realize that the pH is, when it's at neutralized point, the pH will goes to strong acid weak base, so it's less than 7, right? Okay, weak acid and strong base, neutralized point, okay, when they go to neutralized point, the pH will be greater than 7. That's what we learned, right? But so long as you understand why, you will know how to do. Okay? The neutral point definition never changed. Okay? So what happened to this? Why is the pH less than 7? It's because of something called backward hydrolysis, or further hydrolysis, or hydrolysis. Okay? So what actually happens is the nature of the weak acid and the weak base. Okay? The nature of weak acid and weak base is, for example, aqueous ammonia. Aqueous ammonia in ancient time they called it ammonium hydroxide. Okay? But only in this, I think around 12 years, okay? Around 12 years they changed the name to call aqueous ammonia. Okay? So how come they changed the name? Because they realized, right, whenever you have so-called ammonium hydroxide, aqueous ammonia, you never have one of the product. It will always exist in an equilibrium of NH3 with H2O and equilibrium with NH4 plus and OH minus. Okay. Secondly is that if it is majority here, it's more correct to call it ammonium hydroxide. Okay. But if it is majority is in here, then it makes more sense to call it ammonia instead of ammonium hydroxide. Ammonium hydroxide, right? Two different names, right? So last time they didn't know that actually they know it long ago, okay, but they are very, very reluctant to change. So the last 12 years, they finally take a great pain to change back to this. Why? Because this kind of ratios is nearly like 99% to 1%. Okay, very majority of them, they will remain as a dissolved molecular state. And remember, okay, anything that put it into water, okay, it will first turns to, your thing put inside the water, it first turns to the thing's aqueous, okay, and if it can be ionized, it will then split to the positive and negative ion, okay, aqueous. Most of the salt straight away will come to here because this is very ionizable, okay, but we know some cases that they are very soluble but they will ionize. On the other hand, we know that something is very insoluble but they're very willing to ionize. For example, we call it calcium hydroxide. Okay, this is one of the 3 bottles of the strong alkaline. Okay, but we see this bottle is always choky. Okay, why is it choky? Choky because it's very insoluble. Okay, calcium hydroxide is very insoluble. It's very hard to dissolve some chalk in water. Okay, so calcium hydroxide is very insoluble. But for those who dissolve, it's 100% ionized. So long as it's 100% ionized, it's always called a strong axial alkaline. So nothing much to do with how soluble it is. But it is, if for those it dissolve, let's say 1 million particles dissolve 1 particle, or 1 million particles dissolve 10 particles, okay? It's all the 10 particles split to its ion, calcium and hydroxide. If the ionization is 100%, it is always a strong acid of alkaline, regardless how lousy it dissolves. Okay? So strong acid or weak acid, strong alkaline, weak alkaline is all talk about for those who already ionized, is it 100%? Sorry, for those who already dissolved, is it 100% ionized? That is the only question we ask. If yes, strong, no means weak. Okay, and secondly is ammonia. Okay, ammonia is super soluble in water. Okay, this is a very soluble gas. But once it dissolves like ammonia gas, right? Okay, gas, it will actually dissolve in ammonium aqueous, and a majority of them will remain at the molecular state, but the dissolved state. Okay, and one more thing is remember, when we are in mother's womb and fish, okay, we cannot breathe in O2 gas. Okay, no, we can take anything like O2 minus ion. Okay, this is nonsense. Okay, we can only breathe in O2 aqueous. Okay, on the other hand, fish can only breathe O2 aqueous but cannot breathe O2 gas. Okay, otherwise, anyway, we'll die for suffocation. So there's something called dissolved molecular form. Okay, and then it depends whether you want to ionize. Is ionized is another case. Okay, so now understand this. So if you understand the nature of this, right, what will happen if you just anyhow pump in, let's say, 5 mole of NH4 plus ion in water. The idea is that it wouldn't be happy to stay in the NH4 plus because majority of them like to remain in the molecular state. Okay, so it doesn't like to be ionized state. Okay, so what will happen is that automatically you know that you try to tear the water molecules, go back to its molecular state, and throw away the H. Okay, so this is why, right? If you have ammonium ion, it will not want to stay ammonium ion. It will become like that. Okay, because it loves to be in molecular state. Got it? On the other hand, if you give a bunch of CH3COO minus ethanoic ion, it will also try to go back to CH3COOH aqueous state as a dissolved molecule. Because, well, this is quite easy because you know this is organic acid or this is actually a covalent compound. Okay, it doesn't like to be in ionic state. So what happens is that you realize that when you snatch an H, you throw out OH minus. Okay?
So when do we bring the reversible reaction sign?
It's supposed to be reversible for all the weak acid, the weak base things, right? You see, these can dissociate become these, this can dissociate this. Okay? So it makes sense. Okay? But what I'm trying to tell you that if you put this in here, some of them will become this. Most of this will come back here. Okay? But you still have some left there. Okay? If you put this in the water, most of them will come to here. And there are consequences if you come over here is that you have something like this come out from nowhere, okay? Okay? You realize that these things will give me some acid. This one, give me some alkaline, okay? Interesting. Okay? But the idea is that you focus on this guy's nature. Okay? Now, so this is the ions problem, okay? So that when we have so what if it is a strong acid, strong alkaline this way? Now after you react, right, these things, right, is remain as sodium plus and Cl minus. Okay? The point is that the sodium plus and Cl minus is happy with ionized state. It do not like to go back to molecular state. So there's no way they will try to react with H2Os, right? To go back to NaOH and kick your H plus out there. It's not possible. And so therefore no such thing can happen after your first wave of reactions. Okay. This one also, chloride is happy to stay as chloride ion. It will not like to go back to form something called HCl and then will this one with water and give HCl and give you OH minus come out.
So strong acid and base is not reversible.
Yeah, but the reason is the product ion love to stay as what it is. Okay. Now, so when you do weak acid with alkaline, think in this way. The neutralization point will still consider the same instant CH3COOH with NaOH. Okay? So let's break the story to two parts, then it'll be very easy to understand. First part, as what I said, go to the neutralization point. If you want to say neutralize, all acid must react with all the alkaline. All alkaline must react with all acid. And theoretically, at that instant, your theoretical value should be pH 7. Make sense? Okay, good. Okay, so let's assume that you never listen to what your teacher say here. So CH3, COONA, and X and H2O. Okay? Now, so if that is the instant, can I say that it is I would say that if you talk about neutralization point, just nice, you should have the same amount of this pore inside the same amount of this. So when they just react, become this and this. So any more acid here, you gotta say no more. Any alkaline here, you gotta say no more. Any NaOH not reacted here, no more. Okay? Any CH3COH not reacted here, no more. You gotta say this first. Okay?
I thought the CH3
yes, you're right. So,
want to go back.
but you must think this way. Okay? You must think this way. At the neutralization point of time, it's just nice. Okay? Later you know how come this is important. So then the second story is what really comes up. Okay? Is that inside here you have CH3 COO minus ion. And then you have sodium plus ion, H2O, no issue. Okay, so this is happy, it will not change. But this one changed as a second story. So what does it what does it do? It just add with H2O, and will further become CH3COOH back to itself, and with an OH minus. Okay, now this one don't change, right? So this is why one step, just nice, neutral point, pH at 7. Then at that instant, the second step start, in this way. When this equation comes out, you realize you have some excess OH. This is why pH is greater than 7. Okay? And if you take this as a story, you can calculate the pH straight away. Why? Because if you have this, right, okay, I will calculate pH or POH, then you just come out your Ka or Kb equations. Okay? Let's say this case seems like using Kb is better, because Kb reactions, right? So we talk about Kb.
Kb reaction means the original is
Yeah, but anyway, Kb, right, you just say Kw over Ka will do. Okay? No issue. Okay, so yeah.
We see that it's Kb because CH3COO minus is alkali.
Kb, right, reactions right hand side is always OH minus.
Oh,
okay. Ka equation right side is always have H plus. Okay, so look at this, you know Ka or Kb to use. We can still use Ka because you know write the conjugate equation and blah 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 this and that. But I thought you say that it's okay. Those are fun part. Okay. How to write conjugate equations, how to use a conjugate acid and base, those things. Okay, right? Okay, good. Now Kb equation, so therefore you have a CH3COOH, and then you have a OH minus, and then you have CH3COO minus. Okay? Now, if the Kb is of this thing is given to you, or the Ka is given to you, you use Kw dy over and go to find it. Okay? Because Ka times Kw, right? Kw equal 10 to 1 minus 4. Okay? They might not tell you, you just need to know. And so, this is known. So this is known. Okay? So I want to find pH, right? So if I want to find pH of that things, I just need to find this guys. Right? I know this guy and put a minus log, I got pOH, 40 minus pOH equal to pH, right? Okay? So you just want to find this guy. The point is this, so what is this and this? Okay? What is this and what is this? First, what is this first? If you have just now the concept, you know how this equilibrium start. This equilibrium start right after this instant of total neutral point, right? If it's in total neutral point, it is this salt or this ion self-dissociate 1 to 2, right? So if you have one particle OH minus, at the same instant you know you have one particle of this acid. Why? Because the acid in the beginning should all be neutralized at this instant. So you should not have any this thing still remain at this state. So this is why you know if it's split from here to here, you know this and this the concentration got to be the same. Otherwise, you say, oh, in the beginning I add some, did I all go to here, or actually some still remain as this unchanged, so I'm going to add the original portion? No. Okay? So that will tell you that this and this are the same. So therefore, it's justified to say this is OH2 squared. Okay? Only if you have this concept. At this instant, all this are used up. So no more this guy from here. So and here, start from here, so it's self-delivered from one particle to two particles. So these two, the concentration will be the same. So that's you can put a square here. Okay? So how many CH3COO ion is here? Okay? How do you find this? Okay, if you have, let's say you have 1 mole, okay, don't let the word 1, 2 mole, okay? So it got to be neutralized by 2 mole, right? Okay? So if you have this concept, after reaction you got no more mole here. All reacted, right? And you actually form 2 mole here. Make sense? Okay, and then, okay, 2 mole of water if you want water by 2K. Okay? And in this self-dissociation, it starts with, initially, it starts with 2 mole, 0 mole, and 0 mole. Right? And then during the dissociations, you know that there is a X come out, and then you have 2 minus X gone. Right? Therefore, in order to calculate this, right? In order to calculate this, you can use your Kb equal to your
X squared.
yeah. x squared and 2 minus x, if you have this concept. Okay, and the x,
the 2 minus x thing.
the 2 minus x is that because you know this value got to be 2 mole. Because you know right at the neutralization point there, it should be gone. All form these things. So this is the initial conditions for this salt ion. Then you do your traditional one, the thing in front, you'll be able to come up with this. And you know that x is the concentration of OH minus. Okay, find x, okay, you go to concentration of OH minus. Then minus log x, you go to POH. Okay, log 10x, okay, therefore pH equal to 14 minus pOH. Got it? Okay, so after you realize, understand, the idea is just to split them to two situations. Okay, first situation will still remain as what you learn, and then start from this instant you come to the equilibrium. Put it back to the only one equations that you learn. You come up with this.
So this pH is the pH of what?
pH is the pH of the solution after this equilibrium has established, right? Okay, so this will be the pH so-called from the graph of that the true neutralization point. Because the true neutralization point is step 1 plus step 2. Okay, and you find out that with the OH minus you will get something greater than 7.
Then what is this buffer? Then there's this buffer point.
Same thing.
But there's this like, you see there's
Maximum
this,
buffer? Buffer point?
Did it pH of buffer equals to something?
Yeah. Yeah, pH of the buffer. Okay. You think? Okay. Well, let's talk about buffer.
The pH there right, is which point? Is here.
Is the center point neutralization point? Yes, this one.
Yeah.
This one. Yeah.
Okay.
Okay. So, for there's no such thing of okay. Instead, buffer point is actually buffer regions, buffer points. Okay, more than one points. There's one specific point is called maximum buffer point.
Yeah, which
Okay.
is
But you don't learn this, right? Learn buffer first.
yeah.
Learn about what is buffer. Okay. So, is it okay for the weak acid, strong base, those things neutralization point concern? Now, you can challenge yourself if you can do a similar one using ammonia, aqueous ammonia, and if you can use HCl, okay, try to come out the same thing. If you can get more or less how to calculate the pH, if the Kb of the ammonia, aqueous ammonia is given. Okay, if you can solve those questions, that means you're okay with this.
We
Okay.
try one.
Yeah, you should try actually. Okay, try to see whether you can figure out the whole process with NH3 aqueous and HCl. Okay. Okay, you can go through the whole process, find out the pH of the neutralization point. That means you get it. Get ready for buffer things.